Hello everyone, hope all of you are doing good and we are back after a short break. So today we are into our lecture number 24 and we are going to start our new chapter. So this is chapter number 6 in our syllabus. So the sixth chapter deals with the three-dimensional system. Of course, it's a quantum mechanical three-dimensional system. So here what we have already studied is a free particle which is confined in a 1D box, okay, and that we are already familiar of this, and now we are going to extend the same concept here in a free particle confined in a 3D box. So basically we would extend the 1D, means we were concerned about only one direction, this is x. The same concept would be shifted towards the 3 dimension. So let's quickly refresh our memory that in a particle in a 1D box, the potential energy, which is a function of x, was 0. Alright, so within that confinement there is no potential energy. So therefore, according to the Schrödinger equation, we can write this h psi x is equal to e psi x, and here our h operator is only of the kinetic energy operator. So that tells us minus h cross square divided by 2m d2 psi x dx square is equal to e psi x. So this was our Schrödinger equation for particle in a 1D box, and we have to solve it. So same thing we would now going to extend in the 3-dimension box, and here in the 3-dimension box, of course, we will be talking about the Cartesian coordinate. That means we can think about something like this, a box. All right, so here I can define my so let's draw it like this. I can define this as my z-axis, this is my y, and this is x. Alright, so this is this x, y, and z corresponds to they form the Cartesian coordinates, and my particle is supposed to be confined in a 3D box. Alright, so what else is the same thing here. Instead of ux is equal to 0, we now write that u x, y, z is equal to 0. So that means along any one of these 3 dimensions, the potential energy is 0. Alright? And if that is so, then the same thing, now we can write that h psi x, y, z, because now my wave function is dependent on 3 coordinates, x, y, and z, is equal to e, I have to erase it. This is my x. So e psi x, y, and z. Alright. So before we go further, I would just like to tell you that why we are concentrating on a free particle confined in a 3D box, because this model serves as a prototype of hydrogen atom. Prototypes, because suppose in hydrogen atom we can think about that this is a box. Of course it's a spherical box, it's of a 3 dimension, and the electron is to be confined within that spherical box. But only one difference is, though, here it is a free particle confined in a 3D box where the potential energy is 0, but in hydrogen atom we would see the potential energy won't be 0. But that won't change a whole lot of things. We will gradually come to that. So let's now concentrate on here. So h psi x, y, z is equal to e psi x, y, z. Fine. And then we definitely have our boundary conditions. Okay, you remember that for a particle confined in a 1D box, alright, so we had, so this is x is equal to 0 and this is x is equal to a, alright. So our boundary conditions was that psi at x is equal to 0 is 0 and psi at x is equal to a is 0. So psi must vanish at the both boundaries. So similarly, alright, we can define that the boundary conditions means that psi when x is equal to 0 and for any value of yz is equal to psi x is equal to any value for y is equal to 0 and for any value of z is equal to psi for any value of x and y and for any value of for z is equal to 0, it should be 0. Alright. And also definitely psi 0, 0, 0 is also 0. So these are my boundary conditions. So keeping that in mind, how can I write the Hamiltonian operator for a three-dimensional box? So here now we have to write that minus h cross square divided by 2m. Now we have a partial differential equation we have to write because see this is double derivative of psi x, so now we have psi x y z. So we are going to write that the Hamiltonian operator as something like this: del 2 del x square plus del 2 del y square plus del 2 del z square. This would get operated on psi x y z and this should give e psi x y and z. Alright, now interestingly this expression, alright, so what I am now demarcated within a rectangular box, this particular expression is, you see this is an operator, okay, so that particular operator is expressed in terms of this symbol. This is called delta square, and this delta square is called Laplacian operator. Okay. So what is the Laplacian operator here? Delta square is del 2 del x2 plus del 2 del y2 plus del 2 del z2. So in other words, so for a 3D system, my H Hamiltonian operator corresponds to minus h cross square divided by 2m Laplacian operator. Okay, delta square. Okay, so now we have a fair idea that how to form this particular Schrodinger equation for a 3D box. The next question is how to solve it. So since we have been able to solve this one, we can exactly apply the same concept to solve this equation as well. Alright, so let's clean the clean the whiteboard, and let's proceed to solve or directly talk about the solution of this particular Schrodinger equation. Alright, so let's do it. Alright, so this is the equation for particle confined in a 3D box, and we have to solve it. So the best way to solve is the process of separation of variables, and that we have already done it and we are familiar of it. So that means let psi x, y, z is a product of three independent functions of x, y, and z. Alright. So if we now replace this value of psi x, y, z here, and then after the corresponding arithmetical step, we can write that minus h cross square divided by 2m x double prime x of this minus h cross square by 2m y double prime y divided by this minus h cross square by 2m z double prime z divided by z. this equal to E. Alright. So now what we are going to see that the same thing like before, that this is a function of x only, and this part is the function of y only, and this part is the function of z only. So these three independent variables, function of x, y, and z, the summation of these three is equal to E, a constant. Alright. So this means that, of course, so this function should correspond to something like Ex, and this function should give you something like Ey when solving this, and this would give something Ez. So by looking at the overall condition, it prompts me that there is only one way that entire equation can be true if it follows this condition, right? So that means the total energy is equal to Ex plus Ey plus Ez, which were obtained individually by solving this variable separated ordinary differential equation. Alright, and we are already familiar with that how to solve it, and I'm not going to the detailed steps of the solution, but of course it's worth that you give it a try. Alright, so then by solving we can definitely get the energy, and then of course we'll be able to find out the final solution, that is psi xy z. So let's clean the board and write down the final solution psi xy z. Alright, so here if we solve that, we are going to find the solution, that is psi xyz is equal to ax times ay times az. So those are the constant which appears for the amplitude, and these are function of x, y, and z. And so we write sine nx by x by whatever we have these a, b, c, the three the boundaries, okay? So multiplied by sine n y by b multiplied by sine n z by c. Alright, so probably I forgot to mention to define the boundaries. So for 3D, okay, so boundaries are, for x it is 0 to a, and for y it is 0 to b, and for z direction this is 0 to c, and all other boundary conditions remain constant, as I have already discussed, that psi 0 is 0, psi a is 0. For any other values of b and c or y and z, for any other values of y and z, and similarly for psi would be 0 at y is equal to 0, and for y is equal to b for any other values of x and z. Alright, so we understood the boundary conditions, and this is the solution. So where actually the product of ax, ay, and az is equal to 8 divided by a times b times c root over whole root over. Alright, so these are the dimensions in 3D a, b, and c. And then finally we have to write now e. Alright, so here e is now function of nx, ny, and nz. So look here, now we have three quantum numbers now. So previously for one-dimensional box, psi is equal to some constant multiplied by sine n pi x by a, and the overall energy was dependent on n, the quantum number. here we have three quantum numbers in 3 dimensions. So this value is calculated as h square divided by 8m. Now nx square divided by a square plus ny square divided by b square plus nz square divided by c square. Alright. So this is the value for the expression of energy. Okay. So now you see that the energy is dependent on 3 different quantum numbers, x, y, and z. So now as we have understood that how the solution for particle confined in a 3D box came, so now we have to find out, or we have to verify 2 more things. That is, what are the average values? Alright, so average values of what? Average values of position and the momentum for a particle confined in a 3D box. So you have seen that for particle in 1D box, what was the value for the average position? So let's write for 1D box. You remember the average position x was what? If we can take the definition as from 0 to a, alright. So if I take the boundary condition from 0 to a, x is equal to a by 2. The average of x was equal to a by 2. And what was the average momentum? Px, momentum in x direction. Yes, you are right. The average momentum was 0. So now I'm going to extend the same thing for 3D box instead of 1D. So what do you expect? So what should be the average position and the average momentum of the particle in confining 3D box? Alright, so I can guess that you are already telling the right answer, and your guess is also correct. Alright, so we will now erase this part and quickly go through how to find the expression for the average values of position and momentum for particle in 3D box. Alright, so let's do it. Okay, so before we go to the average values, position and momentum, let's take a look. So what are the difference between the position and momentum operator for a 1D box versus 3D box? 1D box, it was easy. The position operator was defined as this x cap, alright? But in 3D, now you see we have 3 vectors, x vector, y vector, and z vector. So how we are going to represent that a vector which is responsible to represent the vectors in all 3 directions. So let the vector or the operator be r cap. So here r cap can be expressed as I multiplied by x cap plus j y cap plus k z cap. So here I, j and k are the unit vectors along x, y and z direction respectively, and your x, y and z are the respective position vectors along that directions. Okay, so once again I, j and k are the unit vectors along x, y and z respectively. So same way, the momentum vector was px cap for 1D box, and what would happen to the 3D box? For 3D box we have now p cap, right? So p cap would be equal to, so we can actually write in the same manner the unit vector. So the momentum operator multiplied by I, which is the unit vector along x direction, plus j py cap plus k pz cap. Alright, so similarly we can write that this px is minus ih cross del del x. Okay, so we can take this minus ih H cross value is there, and then we write that I del x plus j del y plus k del z. Just one thing, not to be confused with this I and that I, because this is the imaginary quantity I and this is the unit vector, okay, and this is root over of -1, okay. So now we are going to calculate our average position and average momentum, okay. So we have our expressions over on the right hand side. So the average position, that is R, okay, is equal to, so we have to bring that sandwich operation. So that means by definition we have now triple integral, because 3 dimensions, 0 to A, 0 to B and 0 to C, and we have now chi star whatever x y z, right, then multiplied by the operator R operating on chi x y z and dx dy dz, okay. So we have to evaluate, so then we have to replace this R cap by this expression and we have to find out what are the values. So if we do so individually, then we can find out, you can try it, the average x is equal to a by 2, and similarly average of y is equal to b by 2 and average of z is equal to c by 2. So as a whole, our average R would come down to I a by 2 plus j b by 2 plus k c by 2. So these are all unit vectors along 3 directions, and a by 2, b by 2, c by 2. So that means the average location is basically the center of the box. So as you have already guessed correctly before even we began to do this, so for a particle in a box, one dimension box, average position is at the center, and for 3-dimensional box, it's a no-brainer. It is again the position is at the center. So now similarly we look for the average momentum. All right. So similarly we have to write the average momentum means average P is equal to, once again, the triple integral 0 to A, 0 to B and 0 to C, chi star x, y, z multiplied by P cap chi x, y, z dx, dy, dz is equal to, so once again we have to expand P operator in terms of Ipx plus jpy plus kpz, and we will find out that individually each of these integrations, because if we expand it, it will break into 3 terms. So we can prove that individually each of these 3 parts is coming down to 0. So overall this is 0. Alright, so the average momentum for a free particle confined in a 3-dimensional box is 0. It doesn't surprise us, because we have seen that for a particle in 1D box, for a particle it has equal probability to go either left or right from the center. Okay, so this is based on a statistical distribution. So similarly, the average momentum for a particle in a 3D box is 0. All right. So now this basically sums up the concept of 3D system. So now one more thing is left. That is, here we would be introducing a concept which we have already seen it classically, but here it is the concept of degeneracy. So remember, this concept of degeneracy was not the part in particle in 1D box, now not in the simple harmonic oscillator. So it is arising here for the first time. how it is. So remember, if my box is a perfect cube, okay, so for a cubic box, A is equal to B is equal to C is equal to A. Alright? So what happens that for the energy expression that we have nx, E, nx, ny, nz is equal to, we have written that expression, right? H square divided by, what was there? Hm, okay? And then we have nx square divided by a square plus ny square. So everything would come down to 8ma square because everything is now a at the denominator. So the numerator part will go like this: nx square plus ny square plus nz square. Alright. So remember, this only happens for a cubic box. Alright. So now for a cubic box, some interesting things appear. So what are those? So if I try to draw those energy levels, right? So here it is E, and we are going to write our n values. So what should be our first n value? All right. So n is equal to nx is equal to 1, ny is equal to 1, and nz is equal to 1. So we can write that the energy values that comes for 1, 1, and 1. All right. This is our first ever energy value, and we have only one set of value. Now what happens if I go to the next possible quantum number? Our next possible quantum number is, one of those quantum number is 2 and the other those are 1 each. Okay, so for that we have this value, all right, 2, 1, 1. But assigning the value of nx is equal to 2 was arbitrary. We could have done it nx is equal to 1, ny is equal to 2, and z is equal to 1, or 1, 1, 2. So no matter whatever we do, we would end up with the same energy value, right? So 2, 1, 1 will have the same energy value as 1, 2, 1, and it will have the same energy value as 1, 1, 2. Now, for 3 different sets of quantum numbers, remember that, for 3 different sets of quantum numbers, we have the identical energy. So these levels are called the degenerate level, and this is the concept of degeneracy, which did not appear earlier for a particle in 1D box and in simple harmonic oscillator. So then you can find it out that there are some levels which are non-degenerate, like 1, 1, 1, and there are some levels which are degenerate, like 2, 1, 1, 1, 2, 1, 1, 1, 2. So now it's your job to find out, say up to quantum number 3, 3, 3, how many of these levels are degenerate and how many of them are non-degenerate, along with their expression in terms of h square divided by 8m square in energy unit. So it's a pretty simple exercise, and you can please follow it up to do it. Alright. Now before we finish today, we would take a look, or rather I would like to draw your attention into another quantum mechanical postulate. So this is not actually the one of the basic postulates that we have already studied in chapter number 4, but this is a pretty general observation, and you can still treat it as another kind of postulate, and it is very simple. So what was that? So just let me write it out and explain to you. Okay, so during the solution of the Schrodinger equation for 3D system, we have gone through this expression, right, as you remember. So let's appreciate the fact that this was our whole Hamiltonian, h psi is equal to E psi. And now you see we have broken the entire Hamiltonian into 3 parts, right? This is our h1, this is our h2, and this is our h3, okay? And not only that, once we solved it, we told you that this is a function of x, and this is a function of y, and this is a function of z. And individually, by applying hx is equal to something, we get the energy. All right, means E1. So from here we got the E1, from here we get E2, and from here we got E3. And that's why we actually, it was possible for us to solve individually X, Y, and Z. And later we took the product of these three to get the final chi X, Y, Z. So from here what we are now observing, that I can write that if our original Hamiltonian can be expressed as something like this up to Hn, alright, and then also if similarly if we can write that H1 chi 1 is equal to E1 chi 1 and H2 chi 2 is equal to E2 chi 2, and similarly we can write Hn chi n is equal to En chi n. If these are true, then as a corollary we can arrive at a conclusion that the individual E1 plus E2 that up to En sums up to E, the total energy. And not only that, the final chi, that is 1, 2, etc. n, becomes equal to the product of the individual wave function, that is chi 1 multiplied by chi 2, alright, multiplied by up to chi n. So here we have a kind of postulate. So in more formal words, I am going to rewrite the statement with a formal general expression. Alright, so that we have learned from today's lecture. Okay, so let's do that. Okay, so here we go. If a Hamiltonian is separable into some smaller Hamiltonian, sub-Hamiltonian operator, if a Hamiltonian is separable, then its eigenfunction, means the eigenfunction correspond to the original bigger Hamiltonian, is the product of simpler eigenfunctions. Alright, so that is what the general form says, that if H is a function of two coordinates, q1 and q2, where this represents the coordinates. Alright, means for a particle in 3D box, q1 is x direction, q2 is y direction, etc. So if H is a function of q1 and q2, and if H can be broken into HQ1 plus HQ2 separated, and also if individually, if H chi q1 is going to EQ1 chi q1, and it satisfies these individual little Schrodinger equations or eigenvalue equations, then obviously the total energy will be the product of those individual coordinate specific energies EQ1 plus EQ2, and also the final solution chi should be the product of the individual chi q1 and chi q2. Alright, the individual wave functions. Or it should be the product of the simpler eigenfunctions. Alright, so these principles can be applied in many places, like in spectroscopy, but we will be not going into the details of that. So basically, today's lecture sums up all the important aspects of a particle confined in a 3D system. So now you can follow the textbook and you can clear your any further queries. All right. So next lecture we are going to review the case for a rigid rotor, which is also a part of three-dimensional systems. So our lectures on three-dimensional system is going to continue for a few more lectures. All right. So till then, I'll see you in the next lecture. Goodbye.